would like to welcome you to a public part of Dan's viva. The viva is done as usual, so there will be a public presentation. It will take around 45 minutes. You will then be invited to ask questions to Dan. Then, after that, we will ask you to leave, because then the private part of the viva will start, and Dan will have his examination. I'm very happy that both external examiners could make it. Kai-Uwe Sattler, who has been here already a couple of times, my dear old friend Manolis, whom I know also for many years. Well, without further ado, to make it in time and not to let you wait too long, I hand over to Dan and enjoy the talk.
Okay, good morning everybody. I'm Dan Leffert. I've been working for Jerry like 5 years and 8 months. Now I'm going to present my thesis that propose a negative and adaptive approach for processing linked stream data. So let's start it with the motivation of the thesis. So the linked data cloud, as we noted here, is completely static in the sense that the data is not incrementally and constantly changed. That means that when the new data comes, you normally have to unload the data and upload the new version. It's really heavy, low operation that you cannot do often that people only can do daily or monthly. And in the dynamic world that you have data from sensor, social network applications, the data always stream constantly and very high throughput into the system. Those data cannot easily integrated together, and there's no infrastructure to enable the dynamic query of the stream data in conjunction with the static data. So we have the integration boundary here between these two kinds of data. So that motivates us to build the unified infrastructure to enable the seamless integration of dynamic data and data in linked data cloud that follow the standardized paradigm of linked data cloud. So with that, will help us to remove the integration barrier between these two kinds of data, and with that, no matter where data come from, no matter where the data dynamic or static, with our abstraction, user only can query the data with one data model called linked data. So our thesis trying to build a fast and scalable linked data stream engine that supports this thing. So in the nutshell, to build such stream processing engine, we normally have to module the stream data in RDF data format in order to integrate with the data in linked data cloud that also in RDF. And we need the clarity query language here to query the data. So normally we have to it had to be compatible with the standardized query like Sparkle, but you have to support the continuous query features in here. So you need a new query language and new query model. Just to bear in mind here, continuous query is different from the one-shot query we have in triple store. We have in semantic web. Because continuous query normally you have to register to the system. It will be running there, and whenever the new data coming to the system, it will trigger the system. So we call persistent query. And then you have to build the processing engine. Following to this step, you need to do some pre-processing to make it faster. You optimize it, execute it, and return the result. That's the informal description what you want to do. But to make it fast and scalable, we have to deal with these 4 challenging research problems. The first thing that, because there are no standardized query there, so you have to come up with the new query processing model that you can model the data. You have to provide the semantic for the query operator, and you have to build the query execution framework to execute this query. And then to make it fast and scalable, you need the efficient organization, efficient physical organization of the data. And then follow up, you need the data structure, algorithm, and of course how to optimize it. But one thing you have to note in here, because the data changes all the time, and the optimization has to be dynamic. So what did we do in the thesis as a contribution is we proposed a new processing model for linked data stream that provide the foundation semantics for our new query language called SQL. And we also provide the native and adaptive execution framework that allow us to deal with linked data and RDF data elements at first class citizens in the infrastructures. And the dynamicity of the execution framework help us to dynamically optimize the query to adapt what is being changed in the system. And by from the new execution framework that allows us also to come up with the novel data structure and the algorithm with that to build very fast query operator to achieve the throughput of the system that we want. And we also come up with some novel algorithm for optimizing the multiple join of the query model that we provided. And the outcome of the thesis is the fast and scalable processing engine we call SQL. And this system can perform around 30 to 10,000 times faster than similar system. It can handle around 100,000 triple per second. It also scale really well in different aspects, like the size of data set we can handle up to 100,000, and we also can handle the window size up to 1 million, 10 million triple in the windows, and thousands of concurrent queries that vary to the system. So come back to the research problems. So now we started with the first one. So how to come up with the new query processing model and the execution framework. So for the processing model, we propose an adaptive query processing model that we provide the formal data model that can capture the temporal aspect, not only the stream data but also the linked data. The processing model that we have provide the continuous semantic for query operators that has 2 parts. The first part is denotational semantics that provide the mathematical formalization of query operators, and they also have the operational semantic that provide the way how the query will be compiled into the the running code at the runtime. And one features that I will present in next slide is the adaptivity of the execution model or the processing model as well. So how the query language look like? So because there's no standard way to express the continuous query for linked data, there are some proposed query language that people propose in parallel with the query we propose. We're well aware about that, but the thing that we concern in here is how to address the sliding window operators and in the new query model, and we also try to minimize the extension that we have to do from the standard query language. That's why we only make the minimal change from the Sparkle query 1.1 that we can address the sliding window operator through the stream keywords and a bit change in the construct query, and we have a new query highly compatible with Sparkle 1.1. With us, we don't care about changing the keywords as syntax or grammar. It's easy to adopt with the new standard. We have the John effort to standardize the continuous query. So another features of the processing model is adaptivity of the execution model. So assume that you have the declarative continuous query like this. We compile it into the logical query plan, and then we have another step to build a set of equivalent query plan that we will be able to change the query during the course during the lifetime of the continuous queries. It is needed for the stream processing because we want to support adaptivity of the query to be able to find the best query when the data changes in the system. So, okay, now we already have the processing model and the query language data model. How we have build the framework to execute that things. The easy way to build the system is, okay, you have some system already out there. It doesn't exactly support all the features that you want, but it has some functionality that you need, like relational stream processing engine, triple storage, that have some part that can satisfy the requirement that you need here. So you can choose delegate the static part to the triple storage to query. You can delegate the streaming part to the stream processing engine. What you have to do is build a query writer in here to rewrite your query, the subquery into the query language that the underlying system support. You have to transform the data in the format that the system can consume, and you need the orchestrator to coordinate the processing. That's all you need, but the problem is you have this. The system had to suffer the overhead of data transformation, and this underlying system is the black box for you. You lose. You have no full control of the underlying system. That make the performance of this system extremely low in comparison with the requirement of low latencies of stream processing engine. You will see you will see them in following experiment that we present in this talk. That's because the most performance gain that you can have is from the knowledge of both part, dynamic and static part, that help you to coordinate the processing of this operation. So we realized that we actually build the system like this to find out what is the problem there, and then we come up with another approach. But before that, we just show you this the more relevant system that use black box architectures, and that we will compare it later. So we have Italics and Gitalis that use Prolog engine as the underlying system to translate everything to, and a Sparkle that use Esper as a complex event processing system, and use Sparkle engine like triple story Jena for that. So what we did is we proposed the SQL execution framework based on white box approach to build the system. If you see in this architecture that we had to rebuild all the components of the system. So why bother to spend that much effort to build that system? Because bear in mind that the system that we're targeting into here is coming from a lot of streaming data source that need the system have to be able to process around up to 100,000 triple per second, and we realized it had to be around 1,000 times or 10,000 times faster than the black box approach that we already tested. And it's critical in the way that if you see, we have to have control to improve the performance in every component of the system. So every component we build in here is about improving the performance, say the memory and whatever to make it faster. So that's why we had the part that employ the dictionary encoding that is well known in triple storage to have a smaller memory footprint, to be able to dynamically optimize the query. We provide two components called dynamic executor and adaptive query optimizer. We analyze and we observe that the static part of the query doesn't change much, so we pre-compute and index intermediate result via the cache manager and the cache fetcher component to do the static part to accelerate the query processing. We also need to have the full control of the window buffer that deal with the constantly change data in the window. That's why we have the window buffer manager that we have full control about internal data structures here. That's the component that we need to carefully engineer and implement the algorithm that make the system as fast as possible. So after we build the system, we evaluate in the first step. The evaluation that we choose here with the scenario that is quite well known, like in the community is social semantic that deployed in ESW 2008. It's this kind of scenario that have been deployed a lot, and there's a lot of interesting and realistic data set that we can get it and replay it to test the system with realistic data distribution. In here, the data set we test is deployed in the conference with around 1,000 people attending conference in 7 days. We also use the DPpedia and SCP Bench, actually the tool to generate the DPLP data set with a similar data distribution that the real world have. So we compare our system with Italis and Sparkle to see how the system perform. We choose 5 represent query that have selection that's very simple filtering, and then we start with simple join and more complicated join, and we also include aggregation that cover most of the query patterns that we need to evaluate. So we conducted 5 types of experiment. The first one we do on the single query to see how fast the query is, and then we vary the size of the LP data set to see how the system behave when we increase the static data set. And then we test with multiple query by register a number of the query that running concurrently in the system to see how the system scale in that aspect. So the result is for the query 1, we perform much faster than C-Sparkle, but we a bit slower than Italis. It's because this system is specialized for filtering, and with the query we only need one component, and of course it's faster. But when the query getting more complicated, and we gain much more better performance in this case. And you see with the more complicated, more join, and we can gain much faster. And with aggregation, a bit complicated, but we still gain a much better performance in comparison with others. So for the next experiment we do in the side of the stream data. So bear in mind this is logarithmic scale, and it's here is 1, but in here 10,000, as you can see. So we have C-Sparkle in the red line, Italis in blue, and C-Sparkle in green. So in most cases, when we increase the size of static data set, our system is really stable. The performance doesn't decrease much. If you see here, the lower is the better because we measure the execution time, the average execution time. Other systems stop at around 1 million triples. There's 1 million triples by the reason that the system run out of memory or crash, and for some other reason. And next is the scalability in terms of number of queries. So our systems scale much better in this case as well. Some other systems that Italis, they stop with less than 10 query for complicated query. It's because like with single query we're faster, and then we have it much scalable than other systems. So for the first research problem, query model and execution framework, we already addressed that. Now we focus on 2 things now. Relational way data structure is not efficient enough. We will solve it later why. And we need the new algorithm with the new data structure we have to commit to make the system even faster. So what's the easiest of using current data structure with stateful window operators? So the railway data structure is not suitable in this case because we have very small data element in our data structure because we already encoded fixed size integers, and we have a lot of data point in the processing, like 1 million windows that have 3 million data point, and we have a lot of that coming to the system and we delete. Another thing is that we point out in our literature there's some other technical limitation in incremental evaluation of query operator as well. One of this distinguishing feature or property of the system of this technique that not suitable for our system because is the auxiliary data is normally bigger than the original data, because if you see in here, we encode everything in integer. So if you add something like timestamp or native tuple, it makes the data much bigger. So to give you intuition how the 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 maintaining processing state is necessary, and the big problem we have to deal with. So for example, we have 3 queries in here, 3 windows in here. We want to join that to have the final result in here. So at the time 2, you have 2 data items in here in the window. So this is the mapping. You see A and B are the variable, the mapping. A1 is a binding value. So this one match, but it doesn't return any final result because the window 3 is still empty. And then you have the new result come in, and you can generate the final result. But the efficient way is you can reuse the previous intermediate result in previous step to generate this one. So, and then you have to, that means you have to maintain that processing state if you want to make it faster. Similarly, other intermediate processing state can be generated during the process. This comes to interesting state at the time 6, that we have the window with triple 2. That means you only can have 2 triple in the windows. When the third one comes, you have to invalidate the oldest one. That means you have to track down all the intermediate result or processing state you already create. That means you have to delete a lot of processing state during the process. And bear in mind, it does generate a lot of traffic and a lot of memory during the process if you don't have a proper data structure. So we come up with a 3-way mapping data structure that that designed for maintaining processing state. Assume that you have 4 windows with a lot of mapping in that. If you want to join this window, you can create a new mapping, but you only have to create 2 pointers to point into original value. Similarly, you create the next one by pointing to what we created. And then with that, you don't have to materialize the value that you have to store in this intermediate mapping. It will save a lot of memory, and it's really fast to track back, to follow the link to get the value you want. It's another thing that the operation you usually have to do is check what is expired. So if something is expired like this, you just follow the link and you find what it created during the process and you delete it. It's easy and fast. So another thing you need to build the index to enable the fast lookup, but you still need to have the low maintenance index because the data update too often. So we come up with 2 indexing schema in here. I don't have time to go in detail. If you're interested, in my thesis we had the algorithm about description about this. To give you intuition how this indexing scheme works. So you have the data coming to the buffer as the bed of mapping. So the data will be deleting in the beginning of the list and will be insert in the end of the list. So the idea of the indexing is trying to avoid the operation on this to avoid the cost of reorganize the indexing structure like tree or hash space. For the ring index one, that's one thing is a bit different from other is we create the ring pointer that allow you to go through the value you want. So the experiment result that we got from this data structure indexing and algorithm associated with that, we can have the throughput up to 1 million updates per second and we can have a lookup around 2 million updates per second. And the incremental evaluation algorithm we have is like perform several order of magnitude faster than relational weight 1, and we overcome all the technical issues that our literature already identified. So far, we already addressed 3 research problems. So we're going to the next one, how to optimize my net. So during the process of building the algorithm and the query operator, we test and we do experiment, we observe the behavior, and we see that the multi-way join dominate the query pipeline. That's that the operator that we need to optimize. So we also give the algorithm for how the multi-way join work. I don't have time to go in detail, but to give you intuition how the multi-way join work. So assume that you have like n buffer as the window. You want to join them, so you can create a symmetric operator similar to symmetric hash join that whenever the new update coming to the buffer, you create the join sequence that you will look up the another buffer and create propagate the result and finally find the final one. In this example, you see you had the update in buffer 1, you update, you go to the buffer 2 to look up for the thing that match and you propagate. So this thing we call propping sequence. So it happens symmetrically in every buffer. So if you want to optimize, you have to optimize the propping sequence because you have like several options to choose the propping sequence. So, but bear in mind here everything happens dynamically, so you have to dynamically choose the best propping sequence. So we mapped from the problem of optimizing multi-way join to the problem of finding the best propping sequence. And we came up with the cost model for finding the best propping sequence in here. The cost model we built is based on dynamic programming approach that we have recursive formula for this. So intuitively that to find the best cost for the propping sequence, you just have to compute all the possible best cost model of the subsequent propping sequence, and it's too expensive to compute, especially in the streaming setting that you cannot afford to spend like millisecond on the optimization part. So we need to come up with something lightweight but dynamic for estimating the cost. So in the thesis, we discovered a nice property for lightweight dynamic cost estimation. We observed that there are 2 typical query shapes that happen in continuous query on the graph-based query patterns. The first thing is the linear sort. If you start from one of the end of the query pattern, you only have one possible propping sequence. That means your result, you've already found the best propping sequence. Another situation is the sort shape that you start from the middle here. You have several options. That's the thing you have to find a way to compute the cost easier. But we find the shortcut condition that allow us to break this star-shaped query into 3 parallel subsequence, and then you do the custom product, and we have the final result, and then you can do the easier optimization or cost estimation here. It provides us the foundation to come up with 1-step and 2-step burst algorithm. I don't have time to go in detail how the algorithm works. The intuitively that 1-step, that means okay, if I cannot go that far, it's too expensive, I just stop here, assume everything fine in the following sequence. If you can go further and go 2 steps or a bit more, if it's cheap enough. So that's for the single query optimization. Another thing that we want to optimize, because we observed that from the experiment that we have, the queries share a lot of the sub-query patterns. So how we gonna share the computation among them? So in here, suppose that we have 3 queries that had the windows on 2 streams, S1 and S2, and how we gonna create a query operator that we can share the computation among them. So we come up with the operator called multi-join operator that we modify for multi-grade join. We add the router in here. So basically, you only do 1 join, but you have the router to route the result to the query you need. For example, here with this result, you have the result that will be routed into the query you want. To give an example how it works in here, so for example, you had a new data item go to this windows. If they found something match, they had to find the window that is destined for. So for example, this one only go for query 3, and for example, you have another one here that match, and it contained in 3 queries, and it go in 3 of them. So that one will work with the query that have the same set of the string they want to query. We generalize that in situation, the query only share the subset of the string. For example, you had 4 queries here, but they share only subset of the string. So we modified that multi-join operator to create a network of join operator so that we can share computation, and then we enable the optimization of sharing computation and optimization with this network. In the thesis, we provide some algorithm and some solution for cropping and routing data. If you're interested, you can have a look at my thesis. It's there. The experiment result that we have from this is for single query optimization. We outperform by order of magnitude from Esper and non-optimized queries. For example, here you see we have 4-way join in a linear and star graph. The more complicated it is, the better we can gain here. And beyond my logarithmic scale in here. For multiple query optimization, we compare with Esper. You see in here, if we add more query, the queries only decrease marginally, but other system going down like this, and then it going handle one query with the environment that we mix 3-way, 4-way joins. This. So far, we already addressed 4 research problems that the thesis identified. So now we put it together and evaluate. By the criteria that we say in thesis statement, we need fast and scalable processing engine. So we choose the social network application domain to evaluate. To be able to do that, we build a benchmarking system that we can generate the social network data, both static and streaming part, that can simulate different distributions, different situation and query pattern as well. This one published in ISWC 2012 last year. For the setup, we come up with 12 queries that cover all possible query pattern of SQL and Sparkle 1.1, and the data will be generated and simulated by the data generator that we built. We conduct the following performance tests. The first thing we measure the execution throughput. Other things we do the test on scalability in different aspects. The first thing is non-stream data size, the size of the static data set, and the window size. The window size. So what does window size mean in here is it means that how much data, historical data that the system can maintain and can look at in the processing. And number of concurrent query, of course, like how the system scale when you have several queries in the system. So for execution throughput, that for the other query that have at least two systems can support that, we had the result that here we can perform 10,000 times faster than C-Sparkle and around 30 to 1,000 times faster than Gitalis. For scalability by data size, you see in here, bear in mind we see logarithmic scale again. And we compare with other systems like C-Sparkle and Gitalis. If you don't see the result in here, that means the system doesn't support the query or it crashes when we test. So we scale very well until 100 million triples, but other systems stop around 1 million triples, and it crash, memory overhead, a lot of things happen. For scalability in terms of query size, again, so how much historical data you can maintain in the Windows. So we can deal really well with the window up to 10 million triple in the Windows, because we have very small and efficient data structure. And you see in here is marginally changed when we increase the window size with other systems that crash at around 10,000 triple in Windows. For scalability in terms of number of concurrent queries, so again, if we increase the query that share the triple, there's some subset of the pattern. When you add the query, it doesn't add much overload on the query, so that's quite stable. When other systems like C-Sparkle crash and other crash at some point in here, around 100 query or something. So far the conclusion is we come up with native adaptive processing model for linked stream data with a new query language and sound clean semantic query model, adaptive and native execution framework that we can deal with RDF data elements at the first class citizen, and also enable the adaptivity to have a better optimization to deal with dynamic data. We come up with novel data structure and algorithm to enable very fast query operator, and we also came up with novel algorithm to optimize multiple multi-way join, and the system that we build as output that can perform like 30 to 10,000 times faster than similar system. We can handle 100,000 triple per second. We can scale up to 100 million triple data sets, 10 million triple windows, and thousands of queries. So some part of the thesis published in around 10 peer review publication in ISWC and Journal of Web Semantics. And this is the name of the paper corresponding to the index we put in the slide. So what we want to do next things we want to do is we want to support display window. That means we can handle that the window that's bigger than the memory could handle. And then we also want to bring the SQL into the cloud infrastructure that we can distribute the processing among the processing node. And another thing, we want to investigate more about more sophisticated cost model for the system, because the system is quite flexible for you to come up with new algorithm and test and to see what works. So far, that's all that I have in the thesis. So thanks to you all for attention.
Okay, we can take a couple of questions. That's it.
I had two quick questions on some of your evaluation results. So on one of the first ones in the table there, it seemed to be, if I got it right, I think it was the first result that you showed, that your engine is faster for more complex joints than for simple joints. Is that correct?
Yep.
Okay, explain it.
Yeah.
I mean, you see it also in the other frameworks, they all get slower, so.
You mean faster?
Okay, yeah, in query 2 you have a value of 3.9, and
Yeah.
then you go down to the other query.
Yeah,
And as
yeah,
far as I
exactly.
got it, these queries are more complex.
The query more complex doesn't mean it's slower if you have the filtering sooner in the pipeline.
Okay, but all the other engines obviously get slower with the more
Yeah,
complex queries.
because like for example, if you have the query that had the static data set is big, they have to scan over. But with us, we index it and then it's faster to filter like.
Okay, maybe ask the other way around. What's the difference between query 2 and query 3 and 4?
Query 2 you only join 2 stream, so you don't have much filtering in here.
Okay, I see.
So selectivity and other things. But in here, if you use the selectivity smarter, and you even faster for faster performance for ticket.
Query 3 and 4 is between stream and non-stream.
Yeah, okay, I got it now. Okay, I see. Okay, the second question on evaluation. When you were talking about your new data structures and algorithms, you said that you have better performance than, I don't know what you said, I think you said relational approach or relational. Then against what did you compare them?
This experiment that we do in execution framework, that we build the framework, we use relational approach for storing data, and we use B+3 and other common indexing systems.
Okay, did you use any relational database or?
We extended Jena TDB. So we use their D+3 index and other. We modified that to make it work. And then with us, we compare. And then we find out that it's not fast as we want.
Okay.
Any other questions from the audience? I mean, the externals will ask a lot of questions later.
I have another one if no one wants. Can you try to boil down, so you said that, okay, there was the need for having this new data model in the new query language, and you developed this SQL, and you said that in parallel there was things like C-Spark were developed. So can you boil down the difference? So what's the difference between both?
In the physics, we found out some different, but not much in terms of semantic. But there's some other systems that have some problem like ambiguity. They don't spot the temporal aspect on the static data.
Okay.
So it's something like, okay, if you run on the static data, you got not support that the data, because the continuous query can run for months and years. You cannot support that the static data is always there. So we also define the temporal aspect that the static data also change. So if they change, you have to reflect that in the output as well.
Okay, but is this something that you only respect in the physical and implementation level, or also
In the semantic
language
as
level?
well and the implementation.
So what's the difference in the language level? So
The language level, when they say that, because the language level you don't see the difference, but when they formalize the data model, so they see that okay, RDF graph and string data with temporal, and that's all. But if you will see this one change, and you have to see that it's the temporal data.
okay.
Probably you can also explain a little bit the ambiguity.
Another thing that the features, we have some other like ambiguity because some people they inherit like, okay, you want to specify the window operator, you just put the stream at the from clause. But we added, we saw that it will bring up ambiguity problem in the query language. And our paper, there's a small contribution, but it's still like the distinguished feature that we had a query pattern that we put next to the where clause that to avoid the ambiguity of the query.
A small question. So when you say like a linked stream data and linked data, do you use the term in the broader like meaning of linked data, which means just data with links, or you mean that these data use HTTP URI, they are published on the web? Does that make any difference? I mean, like, do you make any use of the fact that these linked data?
Actually, we extend this linked data in the same paradigm that you use with linked data. So link stream data item also had the UI activity you want to set to the single stream data element. So it's transparent in the user point of view of linked data. That's the thing we want to have unified. So link stream data and linked data is completely compatible in that way.
But in fact, you are processing RDF data, not link data, right? So you do not follow links while processing queries.
Yeah, that's for identification. So, but if you say that, okay, I maintain the windows, I allow people to accept them. So it's easy to refer from the protocol into the buffer processing, or if we can support display processing, it's easy to go to history to retrieve the data item.
Jose, do you have another question?
I would have one if you want.
My question for them.
Okay, really last one. You said that's more out of personal interest. So you said that for the last evaluation, or complex evaluation, you sort of evaluate or you generated social network data.
Yeah.
What is do you simulate user activity, like posting behavior, or what is it
Something
actually?
like that. Actually, called Dancing, I didn't include much in the work because it's a collaboration work between me and the group in Amsterdam that do the mapping system for social network and theatrical bonds, I guess, and another group in Vienna. So it's a joint work for creating, and then they do the simulation part. So the new thing in the simulation platform that we publish in ISWC is we simulate the behavior by the windows.
What?
So if you see like the distribution of the data when you simulate the behavior by posting things, you don't. The previous one they don't consider that like by window by time. So we generate by. We have a protocol window-based generate data simulation. So by time by day you will see the distribution in that effect, and we have parameter to change that. Because if you do the continuous query, you have to see that distribution between the window and other things.
But you simulate user behavior in there.
Yeah, they post like if they go around, they live in Galway, they mostly posting around Galway,
Okay.
place in Galway. It's another thing, it's not different things.
Yeah,
I
sure,
use
sure,
that,
that's why I
but,
said
yeah.
it.
But I'm the one that come up with requirement, and the other group try to do the simulate. We model the query and the behavior.
And there's a paper on that, you said.
On that, we published in ISWC
This year or?
last year,
Last year.
2002.
Okay.
20.
12, yeah.
12.
Sorry, John. No, they take too long.
Just a quick question. What was the implementation of the join? How did you implement the join operations there?
Here we explain. We have in the thesis we explain the John algorithm really greater detail, but we don't have much time.
I was just asking about the implementation.
Yeah,
we
Let me show you.
The language or?
No, implementation of the John. So instead of people usually do binary John, we generalize that multi-way John. So this is that we employ some algorithm for semantic hash, multi-way hash John for this, and this is the algorithm that we can deal with like multiple John that we group in together and we have a lot of detail about algorithm, how it works, how to propagate this thing, and how you can inject the optimization inside the joins. Yeah, so with that, if you think that you can have better optimization than mine, you can extend my framework. Actually, our framework is we will bring the open source tools. You want to play around with us.
Did that answer your questions, or did you want to know something different?
Yeah, I think I have to refer to people.
Okay.
I have a simple question. Your improvement over time, is it basically because of the index string structure or your algorithm behavior? Like, can you explain?
Both. So
Which
if you had a better,
contributes like to more efficiency, like the index or the algorithm, or
and here we have both.
Like
The
other
indexing
system-
system to help you to do faster operation. The algorithm to help you to do have a smarter way to compute the data. For example, like if you do aggregation incrementally, you have a smarter way to go back to something you already computed, because it's string data that are coming into the system. You don't know what happened next. So if you have a smarter way, like okay, if I already compute that, I leave it there, and if you have used and need to use it later, just go from that step. I don't have to go back that far to recompute to have it. So for example, you do average computation incrementally. So how you have a new update, you just do some simple computation and you have a new result. Other than go back through 1 million data item in the window to recompute.
so like
So both
other systems they didn't use indexing.
they use, but different ways. So in the thesis we show that why it's faster and why it's not efficient. In here because the environment is RDF data, so the way that we organize the data have to be somehow connected to the graph data, RDF data.
Okay, I think there are no more questions. Then